Hi, my name's Arun, and in this video, I'll be going over our paper privately answering counting queries via generalized Gaussian mechanisms, and this paper is joint work with Jiazheng Zhao. So in this paper, we consider the counting queries problem. So in this problem, we're given a vector D, which represents some statistics about a database containing users' private data. And our goal is to find the mechanism that outputs a noisy copy of the vector D. We'll denote the distribution MD, such that this mechanism balances the goals of privacy and utility. So for privacy, we want epsilon delta differential privacy, which basically says for two adjacent databases, that is databases that differ by at most one individual, the distributions given by the mechanism satisfy some statistical closeness. So in particular, in the counting queries problem, the vector D, each coordinate is the count of the number of users in the database that satisfies some property, more or less. And so for two adjacent databases, their corresponding vectors, the difference between the vectors will have L infinity norm at most one. Okay, and then the utility guarantee we want is that M has low error. And what do we mean by low error? So classically, and what's well understood, the error was the L1 error. So the L1 error is basically just the expected amount of noise we add on average to each coordinate of D. And here the Gaussian mechanism, which just takes D and then adds noise sampled from a Gaussian, achieves the optimal error of root k log 1 over delta all over epsilon and satisfies epsilon delta differential privacy if the standard deviation is set correctly. So what's been less well understood until recently is instead the L infinity error. So what the L infinity error is rather than look at the expected amount of noise we add on average to each coordinate, we look at the expected amount of the maximum amount of noise added to any coordinates. That is, we look at the expectation of the L infinity norm of the noise vector. So here the Gaussian mechanism loses a root log k factor because for a k-dimensional Gaussian, the absolute value of its largest coordinate is going to be roughly root log k times larger than the average absolute value of its coordinates. So the question that we hope to address in this paper and that other past and future papers address before and after ours is whether it's possible to avoid losing this root log k factor. So in our paper, we consider instead of using the Gaussian mechanism, which adds Gaussian noise to the vector, we use a generalized Gaussian mechanism, which adds generalized Gaussian noise to the vector. And what is a generalized Gaussian? Well, the Gaussian has a PDF that's proportional to exponential the negative L2 norm squared. And all a generalized Gaussian is we take the 2 in the norm and in the exponent, and then we just replace them with a parameter p. Now, why does it make sense to use this noise distribution for the counting queries problem? So here I've plotted a Gaussian with sigma equals 1, and then the generalized Gaussian with shape 8, and also sigma equals 1, in blue and purple respectively. And you can see that the purple distribution, its PDF has a much sharper tail bound. That is to say, we should expect that for k-dimensional generalized Gaussians, its largest coordinate is going to be similar in magnitude, more similar in magnitude to its average coordinates than the Gaussians. However, there's a little bit of trade-off, which you can also see in this graph, where the PDF of the generalized Gaussian takes a longer time to actually noticeably fall off. So this means that while we have a better ratio of worst case to average coordinates, we're probably also going to have larger average coordinates when we compare to the Gaussian mechanism. So we'll just finish this video by going over our results. So what was shown by Sankei and Ullman in 2017 is that the L1 error, the optimal L1 error achieved by the Gaussian mechanism is also a lower bound on the optimal L infinity error. And some future papers actually show this was the best possible error after ours. And so what we show is that the generalized Gaussian mechanism with shape parameter p has error that's oft times root p times log k to the 1 over p, assuming some mild assumptions on p and delta. And additionally, if we compose this with the sparse vector, we get error where the log to the 1 over p of k gets replaced with log k to the 1 over p. And then if you optimize for p, the first result becomes oft times root log k, and the second result becomes oft times root log k. So besides the quantitative results, what is really more qualitatively interesting about our paper is that it is the first closed form analysis of the generalized Gaussian in the DP literature. And in particular, while there have been future results improving on the L infinity error of our paper, there are some qualitative reasons why a generalized Gaussian might be more appealing than those results. So our hope is that following this paper, there will be more analysis of the generalized Gaussian and more investigation into where it could improve upon the Gaussian, both in theory and practice. All right, thank you so much for watching, and I'd be happy to answer questions during the conference or offline.